Hello. We have about half of chapter 2 to cover. This section on instance center. Before we do so, I'm going to play this animated GIF available on the 4-bar linkage Wikipedia article. It's something I uploaded. It shows a crank rocker 4-bar. Link length are 6, 3, 7, and 5, and it displays the input angle, it displays the transmission angle, and it displays the output link angle, and it pauses at the minimum maximum transmission angle positions. So this is the minimum transmission angle, minimum output angle, and then it pauses again when the transmission angle is maximum. Just observe these values, and then it pauses again when the output angle is maximum. Hopefully with this additional information you will be able to correctly answer quiz question, exam question of the type draw a certain 4-bar in its limit positions and its minimum maximum transmission angle positions. Okay, so let's switch to the notes, and the notion of instant center of velocity is not new to you. I know you have seen it in dynamics. There you looked at the particular case of the instant center between a moving body and a stationary body in 2 dimensions, and these are 2-dimensional concepts. For 3-dimensional motion, it's a bit more involved. It's called screw axis, instantaneous screw axis. Okay, so how do we find instant center? It's a body that is common to 2 bodies in relative motion. One of them could be stationary or both could move, and does not have to physically belong to the body. Could be outside of the body again, but it's overlapped, and instantaneously it has the same velocity whether it belongs to one or the other of the body. If one of the body is stationary, of course it means that the moving body has instantaneously a point of 0 velocity, and this is what you looked at in dynamics. Also called centros or poles or velocity poles. The analysis that we'll be doing, we're going to identify what I'll call readily available, directly available instant centers. These will be centers of pin joints or line to infinity perpendicular to the lines of sliding or prismatic joints. And then there are instant centers that are not directly available, and we can find them through an analysis we'll learn about in this section. Concepts are a bit abstract to some students, but they are useful in velocity distribution analysis, force mechanical advantage calculations, cam follower and gear mechanism theory relies on instant centers. It will be the theorem of fundamental theorem of gearing, and then in the design of suspensions of automobiles. Recording the instant center with respect to one or the other of the bodies result in what are called centroids or poloids. Remember poloids, and they're useful in, here it says, kinematic equivalence and path curvature analysis, biomechanics of joints of humans and animals, and so forth. Again, we'll be in the analysis that we'll be doing, we'll be looking at all instant centers. It is taking all possible pair of bodies in a mechanism, which means that for an n-link mechanism, we take combinations of n or it'll be combination of n taken by 2. This is the formula to calculate it. 2 factorials. Could have skipped the factorial sign. And this means that for a 4-link mechanism, if you make 4 times 4 minus 1, 3, divide by 2, that's 6. And likewise for 5-link mechanism, there are 10 instance centers. For 6-link mechanism, there are 15 instance centers. 7 will be even more. Okay, so in the analysis, in the instance center analysis, we're going to make use of what is called Arnold-Kennedy theorem, which states that any three bodies in plane motion, connected or not, one of them could be stationary. There will be exactly three instance center. That's something that we agreed upon early, but the valuable part of Arnold-Kennedy theorem is that these 3 instance centers will be on the same straight line. Very powerful. So you take 3 arbitrary bodies in not connected in 2-dimensional motion. They have instance centers between each other, so there will be 3 in total, and these 3 instance centers are collinears. As the mechanism configuration changes, the location of the instance center changes as well. So that's why instantaneous instance centers of velocity. First example consider is that of a 4-bar linkage. So we have 4 bodies. 4 bodies means that we have 6 instance centers, and in total, and of these instance centers, 4 are readily available, or obvious instance centers, and those are centers of the pin joints. They are labeled here. I12 instance center between the ground and link 2. Could use the index in reverse, like 2-1, but it's the same thing. Instance center between the ground and link 4. Instance center between 2 and 3. I23, and between 3 and 4. Looks like I'm missing a labeling for link 4, so this will be I34. Okay, but then there are instance centers between 3 and 1 and between 2 and 4, and we cannot tell directly where they are, but we can find them by using Kennedy theorem. To keep track of the existing instance centers and what we need to do next to find a missing or instance center are these diagrams, circle diagrams. So you position about equally spaced dots, 1 per body of the mechanism that you are analyzing, and once you find an instance center, you connect the respective bodies. So I have 1, 2. I figure out where it is. I draw the line that connects 1 and 2. Find 2, 3. Draw the line between 2 and 3. 3, 4, and 1, 4. Okay. Now this diagram also directs or helps us directing our search. So here, missing are instance center 1, 3, and 2, 4, and the order in which we find them, it's not. Can be found in any order, either 1, 3, or 2, 4. But in general, you're looking at, in order to progress with the analysis, you're looking, and this is important, so you want to pay attention. You're looking at triangles that miss one side and they share that side. Why is that? Because we have 1, 2, and 4, 3 bodies, and to the 3 bodies it corresponds of a Kennedy line, and then we have another set of 3 bodies, 2, 3, and 4, to which correspond the Kennedy line. The missing instance center will be found at the intersection of the 2 Kennedy lines, 1, 2, 4, and 2, 3, 4. So let's see how it goes. Let's say we're looking for instance center between 1 and 3, or 3 and 1. So with the theorem that we learned about, to apply it, we go like connecting instance centers 1, 2 and 1, 4. Oh, I'm sorry, I should look here. So we're after instance center 1, 3. So we connect instance center 1, 2 and 2, 3 and extend that line. And then we look at the other triangle that's sharing a missing side, was the first one. So we have instance center 1, 4 and instance center 3, 4, and we extend that line, and that will be Kennedy line 1, 3 and 4. The other one was 1, 2 and 3. Where the two, and we know that along this Kennedy line there should be the instance center 1, 3, and it should also be along this other line 1, 3 and 4. In order to satisfy both requirements, should be the instance center that we're looking for, I1, 3, should be at the intersection of the two Kennedy lines. So we have one figured out. There's another one left to find, and for that we do the same. So we're dealing with Kennedy lines 1, 2 and 4 that we're going to intersect with Kennedy line 2, 3 and 4. How do you draw Kennedy line 1, 2, 4? Well, you take instance center 1, 2, an instance center, so 1, 2 and 1, 4, draw a line, and then we go with instance center 2, 3, this one, 2, 3 and 3, 4, draw a line, extend it. Where the two lines intersect, there's the instance center 2, 4, because it has to be all on both lines, so it can be only at the intersection of the two that thought for instance center. Okay, and this explains all the steps that we took, and the next example in the notes is that of a slider crank mechanism. And with slider cranks, it's a slightly different take for sliding pairs, that is prismatic pairs. So same with the 4-bar, we have the ground link 1, 2, 3 and 4, the slider, and we know that the instance center between ground and link 2 is at the center of the pin joint. This is the other instance center between 2 and 3. Instance center between 3 and 4 is like right here, and instance center between 4 and the ground, it's going to be on a line or at infinity, going to infinity along the line that is perpendicular to the line of sliding. And this line of sliding or the perpendicular can be drawn anywhere where it's useful. I have it here. You can see oversized slider block, and I drew the perpendicular somewhere in an at one end. Could be anywhere, really, just like a reference direction. So let's see how I proceed with this slider crank. To say find instance center between 1 and 3, I'm here. We're going to draw Kennedy line 1, 2 and 3, and Kennedy line 1, 4 and 3, where the two intersect is the missing instance center I1, 3. So 1, 2 connected with 2, 3, extended, and then you go instance center 1, 4, and 1, 4, it's at infinity, and you want to draw it through the other so 1, 4, okay, and 3, 4. So we have 3, 4. We know we can put our finger on it, and then we draw the 1, 4 line, the perpendicular line, through I3, 4, and extend it. And where the two intersect, we have I1, 3. Okay. There's one left. So to find the last of the 6 instance centers, we're looking at these two triangles with a common missing side, and we're working with Kennedy line 1, 2, and 4, and the other Kennedy line will be 2, 3, and 4. So 1, 2, 4 Kennedy line goes connects point 1, 2, and then connects point 1, 4. So 1, 4, it's at infinity. So we take the same line that is perpendicular to the line of sliding, and we translate it, move it to where it goes through 1, 2. Okay, so this is the Kennedy line 1, 2, 4, and then the other Kennedy line I said connects 2 and 3. So I have 2 and 3, and then 3 and 4. So draw the line, and where it intersects the other Kennedy line 1, 2, and 4, you have the missing instant center 2, 3, rather 2, 4, the one that's shown in dashed line. And this is it. Okay, now, and things are explained here in words, the steps to follow. The case of contacting bodies, so you have a cam follower pair or a pair of gears. We're assuming that the contact is made where the surfaces are smooth. They have there is a common tangent, there is a common normal, and so smooth surfaces with first and second derivative. The two exist, and then this circle diagram indicates there's just one missing instant center between 2 and 3. So we have 3 bodies. We know instant center I 1, 2, draw a line. We know instant center I 1, 3, draw a line. Missing is 2, 3. So Kennedy theorem tells us that the instant center can be found through intersection, but here we don't have a or we need to go a little bit a different way. So one possibility is to draw what is called the equivalent 4-bar. So we know the center of curvature of this surface about the contact point, and likewise we know the center of curvature of the other surface about the contact point, C2 and C3. And just around this position of the cam follower of these two contacting bodies, I can draw what is called the equivalent 4-bar. I can find an equivalent 4-bar. So how to get the equivalent 4-bar? You connect the ground links with the center of curvature, and there's where the coupler goes. It says equivalent 4-bar because around this position, a little bit to the left, a little bit to the right, contact maintained. This moves a little bit to the left, a little bit to the right. The relationship between the angle of body 2, angle of body 3, it's satisfied also by a 4-bar with this configuration. That's why it's called equivalent 4-bar. And we know how to find instant centers in 4 bars. So we're after instant center 2, 3. Kennedy line, where the two intersect, you have the missing instant center. You don't need to go through this process. Another way of doing it is just to show the common normal. Easiest to draw first the common tangent at the contact point, draw perpendicular to it at the contact point, the common normal, and then you intersect that with the line of centers, and it gets you the missing instant center between the two moving bodies. Okay. So this is one case. You could have pin in a slot joint, including with curve slot that you analyze the same way. Yeah, we're good to look at some applications. One application of instant centers is in the design and analysis of vehicle suspensions and the vehicle behavior during turns. So we have a mechanism that it's guiding the wheels. Wheels make contact to the ground, and we're assuming the contact points to be pinpoints. And also in a reference position where the body, where we have symmetry, mirror symmetry, the instant center that we're after is the one between the car body and the ground. And we can do the analysis for both front and rear axle. And rear axle, say rear axle is usually goes the other way, so we can have a 4-link suspension, double A-arm suspension to the rear, and we can have a McPherson to the front. We find the instant center of the car body relative to the ground for the front, and likewise for the rear. And then the line that connects the two, it's called the roll axis of the vehicle. So let's see first how we can get the instant center. I said that the contact point between the tire and the road is assumed to be a pin joint. And then you can see some Kennedy lines that have been drawn. This yields an instant center between the wheel and the chassis. And then you connect the Kennedy line again. We know that these three are collinear: 1, 2, 1, 5, 2, 5, 1, 2, 5 Kennedy line. And because of the symmetry, I mean, you can continue the same. Extend these two lines, which is shown here for deflected suspension, and then connect the instant center between the other wheel and the chassis with the contact point. And the intersection of the two gets you the instant center between the chassis and the ground. Now, in the reference position, when there's symmetry, you just intersect this Kennedy line 1 to 5 with a longitudinal plane, and we know that the instant center is going to be there. Okay, the case of a McPherson suspension, remember you have instant center between 2 and 4 at infinity on a line that's perpendicular to the line of sliding of the this suspension strut, and following the same approach. So Kennedy line 2, 3, 5, Kennedy line 2, 4, 5 gets you instant center 2, 5, and then you connect that instant center with the contact point to the ground. This is Kennedy line 1 to 5, and in the reference position is on the longitudinal plane. Or if it's a deflected case, this chassis is tilted and turned due to the centrifugal force. The instant center between the chassis and the ground is, as you can see here, off the longitudinal plane. I mentioned roll axis. The one that connects instant center for the rear suspension was the instant center on the on the front suspension. Ideally, that should be pass through the center of mass of the vehicle. If it does, then the amount of roll of the car body during turns caused by the centrifugal forces, it's going to be minimal. And I do have this is a screenshot, a simulation showing a simplified model of so this would be the left suspension, this would be the right suspension, and then there's the car body. And as you look here, you have 1, 2, 3. This would be the instant center between the car body would be and the ground. And if I have this side force equivalent to the centrifugal force that develops when the vehicle moves in a turn, so if it's right at the instant center, the system does not deflect. If it's elsewhere, the system deflects. So let's look at the actual working model. I have it here. Let's start with an arbitrary position. I hit run, and this would be again the case of a suspension that is not matching the. And of course, as the loading of the vehicle changes, center of mass changes. Some variations are, but if they are too far apart, the line of the roll axis and the center of mass, this kind of things can happen. That there's a lot of roll of the chassis during turn. Now, if I move this, the instant center between the ground and the car body, you can see that very little happens. Okay, let me go to rolling disk. Well, disk first. So it's working model, and working model can show velocity vectors of points, and you can see the velocity distribution, something you saw in dynamics. I'm sure you've been told about this. And then I'm looking at the rolling disk, and it rolls without slip on a along a rectangle, and the instant center between the rectangle and the disk is the contact point if there is no slip. Okay, and if I record the contact point, that is the instant center between the two bodies, relative to the ground, then I get the ignore the set point. So I get the fixed poloed or fixed centroid. If instead, if I move my observation point on top of the disk, so new reference frame, and on the circle, if I hit run, then you can see that the locus of the instant center between the ground and the disk is along the circumference of the disk. And one thing about centroids is that they appear to roll without slip on top of each other. So I'm going to Wikipedia, or maybe back to 4-bar, and here I have an animation of the fixed and moving centroids of the coupler relative to the ground of a 4-bar, and as you can see, they appear to roll without, like a hook moving along some curved surface. Okay, so this is purple as the fixed centroid, green is the moving centroid. It moves together with the coupler, and this is a drag link. Remember, all three links perform full rotations, including the two adjacent to ground and the coupler. Okay. All right. So let's go back to the notes and look at other applications, or some applications. And I apologize for the background noise. This sample problem explains how you can find the instant center of this quick return with an eccentricity. And we have 4 bodies, so it'll be 6 instant centers. Instant center between ground and link 2, between ground and link 4, between 2 and 3, and then at infinity, perpendicular to the line of sliding, we have the instant center between 3 and 4. This is an elbow rather than a sharp corner on purpose, because in the past I had students considering, for no clear reason to me, that corner as an instant center. It is not. Okay, so, and I'm even labeling Kennedy lines. As you can see, AK 1, 2, 4. So 1, 2, and 1, 4, 1, 2, 4. If you connect points that belong to more than 3, other than 3 or together, other than three bodies, that's not the Kennedy line. So if I'm to connect, say, this point here with this point, I'll have four bodies contributing instant centers. I have 2, 3, and 1, 4. So it'll be 1, 2, 3, 4. This is not a Kennedy line. Okay. Missing is the circle diagram, but I'm sure you can follow. This is a cousin of the slider crank, and I would say it's easy to understand. This is a more involved example of a mechanism with pin in the slot joints, and the slots could be other than straight, but here they are shown rectilinear. And we have only four bodies, but finding the instant centers requires some thinking, because we have only 1, 2, and between readily available instant centers. So between 1 and 2 is right here. Between 1 and 3 it's right here. Between 1 and 4 it's perpendicular to the line of sliding at infinity. So we call that a known instant center, even if we cannot put our finger on it. And then there are two instant centers between body 3 and 4. Here's a pin in a slot. There's a contact. Remember the cam follower type contact. And the instant center, we know that is along the common normal. So common tangent is depending on which direction it moves. So it could be either this or this one. Perpendicular is the common tangent, the line of action. And but we don't know where it is. We know the direction, but we know the we do not know the location. And then similarly here, the instant center between 2 and 3, it's on the common normal here at the contact between the pin and its slot. So on this circle diagram, solid thick lines are instant centers that are unambiguous, and then with thin lines I have the instant centers that are we know only the direction along which they are located, but not their exact position. So the analysis has to take into account that we are having actually 1 and 2 could be found instant center 1 and 2 and 3. These is the succession. I shouldn't have said instant center 1, 2 and 3, but rather instant center 2, 3 and instant center 3, 4 can be found at step 1, and then instant center between 2 and 4 could be found only after finding these other two, 2, 3 and 3, 4. So this is with colors. This is the diagram. Remember, common normal. So again, studying what it's here, and with the comment that you need to find instant center 2, 3 and 3, 4 before you can find instant center 2, 4. I would say it's enough for your study. Okay, other applications of the instant center are for velocity analysis and mechanical advantage analysis. I'm sure in dynamics you did problems where you looked at instant centers as a helper for velocity analysis. You'll see that there are more powerful tools, but for mechanical advantage analysis, say this could be of use. So I'm showing here a cam follower pair of some sort, where body 2 is the input, body 3 is the output. I have an assumed input velocity, angular velocity, and also I'm loading it with a resisting moment, and I work against the resisting moment with an input moment. The input moment, it has the direction of input velocity. The resisting moment opposes motion. So you can see that. Oh, I need to flip this. Sorry. So I'm going to redo or change this figure and flip the resisting moment. Okay, so we learned that the alright, so what I did, I paused the recording and I made some changes to the drawing. There was a mistake, and other than the resisting moment not opposing motion, but link number 3. So we know how to find the instant center between body 2 and 3. We just extend the common normal and intersect it with the Kennedy line 1, 2, 3, the line that connects the two ground joints, sometimes called the line of centers, at least for gears. So assuming that the geometry is fully known, and we can draw on paper or CAD these lines, and we can find their intersection. We can measure any distance we want, say from here I23 to I12, and from here to I13. So that's considered given or feasible, and we can write now these two equations. So we know from theory that the instant center has the same velocity whether it belongs to body one or the other of the body. So instant center I23 from the perspective of body 2 will have a velocity equals to omega 2 times the distance from I12 to I23. Now from the perspective of body 3, the same instant center has velocity equal to distance I13 to I23 times omega 3. These two are stated here, and I'm telling you at this point that I will need to flip the omega 3 arrow and yet again the resistant moment. Why? Because looking at the given input omega, that is omega 2 known, the velocity of 2,3 will be upwards, perpendicular and up. And in order for that same to apply from perspective body 3, I need to have omega 3 clockwise, same as this one. And it holds reason because just imagine these bodies pushing each other. There's body 2 pushed as body 3, and this tends to also move to the right as body 2 rotates clockwise. Sorry for this. So we take these two equations with a limited velocity between the two. We agree that this is the same, and it gets us the velocity ratio, angular velocity ratio, input velocity over output angular velocity. It's the ratio of these distances, which can be measured on the drawing. Now, so this approach allows us to calculate the velocity of the output body 3, that is omega 3, given omega 2 for this considered configuration of the system, which allows us to find draw the common norm. Furthermore, you can, or we can, calculate the input-output, the input moment and output moment ratio, which is the mechanical advantage. So mechanical advantage is the resistant moment over input moment, and we're assuming that there's no significant friction between the two bodies as they slide. They're well lubricated, so the power is conserved. There are no losses. Work is conserved. Work per unit time is conserved. That is power. Input power equals output power. Input power is the input moment times input link angular velocity. Output power is the resisting moment times angular velocity of the respective link, output link. So from here we get the ratio resisting moment over input moment as omega 2 over omega 3, which we found it early as being the ratio of these distances from the drawing. So this length over this one, and voila, we have the mechanical advantage calculated as a ratio of two distances can be measured on the drawing. All right, another example is that of 4-bar mechanism with the input link number 2, output link number 4, and here I'm also showing some velocity, so orientation of these arrows are correct. So if we want to find, again, for this position, we know link lengths. We know the angle of the input link. So position problem is solved. We know the angle of the output. We have this configuration given. We can measure anything that we want. You will see it's a matter of finding the instance center between link 3 and the ground, I23 here, which for brevity it's called just I, or is labeled I. So we can calculate omega 3, we can calculate omega 4. How do we do this? So firstly, find the instance center. We've done this earlier. Just connect or draw the two Kennedy lines where they intersect is the instance center between body 3 and body 4. And then we're having we know that in this position, body 3 appears to rotate, to perform a pure rotation, but only momentarily about instance center. So relative to the ground, this body 3 appears to rotate about this point. And we know the direction of velocity of point B, which is instance center between 2 and 3. We care less about that. And likewise of this one. So they will be perpendicular to these two lines, the perpendicular sign. And we can also say that, or write what VB is. So VB, from the perspective of body 2, is just going to be distance AB times omega 2, but it's also equal to this distance I to B times omega 3. So this allows us to calculate omega 3. And now that we found omega 3, we can move forward and say velocity of C is this distance times omega 3, which we found previously. And ultimately we add that velocity of point C is the length of link 4, that is distance CD, multiplied by omega 4, which is not known, but knowing VC we can calculate omega 4. Everything is stated here. So velocity of B from the perspective of body 3, velocity of B from the perspective of body 2, and of C from the perspective of body 4, as well as from the perspective of body 3, or here, and find omega 3, and then we can find omega 4. If we want to write calculate mechanical advantage ratio between resistant moment and input moment, we need to take the ratio between remember was omega 2 over omega, input omega over output omega is omega 4 in this case. So, well, it's restated here, that power conservation, and yeah, ultimately mechanical advantage in the 4-bar is this fraction here. So have the instant center, you measure some distances on the figure, you can find mechanical advantage. Of course, we can calculate mechanical advantage if we know omega 4, and this is something that we'll learn how to do in chapter 3. And if you have omega 4 and you know omega 2, you can also calculate mechanical advantage without going through these steps. Okay, there are some few pages of examples, or rather questions and exercises from the earlier part of the chapter, like checking if a 4-bar mechanism can assemble, if the link number 2 it can perform a full rotation. We are going to stick with this standard drawing for a 4-bar. R2 is usually the input, and the ground link is horizontal. These notations A, B, C, D, R2, R3, R4, it's not shown here, but this is going to be omega 2, this is going to be omega 4. Okay, and back to the problems, the end of the chapter. So likewise for the slider crank, we have some problems. The R1 would be the eccentricity. Notations go back to the beginning of the chapter. Again, eccentricity R1, crank is R2, connecting rod is R3. I'm not going to emphasize the design problems where you need to find some link length that makes the mechanism crank driven, or it's more like analysis. So all given show or verify if it's slider crank or crank slider. The oscillating slide case for a mechanism to assemble remote a triangle inequality. And then time ratios, a strict or direct application of the formula. Look at the example in the text where I'm asking you to find the limit positions and time ratio given this kind of input-output graph. And then transmission angles and limit positions for given link lengths, also straightforward application of the equations. There'll be a homework assignment where you'll have a chance to practice. Now, okay, what says, is this mechanism prone to jamming? Of course, you evaluate the minimum transmission angle, maximum transmission angle, see if their deviation from 90 degrees is more than plus minus 45, and you can make your statement. Again, we can go plus minus 6 degrees from the ideal value if there is some help from gravity or from elastic spring. Instant centers, two bodies in contact, find the common normal. We go with the common tangent, it's easier. Common normal, Kennedy line, 1, 2, 3. So I have 1, 2, and 1, 3, 1, 2, 3, yes. Okay, some instant center examples. So let's look at this one. I could do just this, or I'm going to take a screenshot. I'll go to Paint, and let me pause this. Alright, so I paused the recording, and we're going to look at finding the 4 instant centers for this mechanism. It's the quick return mechanism, and we said that we need 4 transparent. Let me pause again because it takes some time to draw the circle diagram. All right, so I have the circle diagram. Each of these dots represent a body. I have instant center available, instant center between 1 and 2. So I draw the line. I have instant center between 2 and 3. I draw the line. I have instant center between 1 and 4. I draw a line. And between 3 and 4, this is going to be at infinity on a direction that is perpendicular to the line of sliding. Okay, between 3 and 4. So also connect, and I made this thinner. These two. Okay. So I can proceed with any of the calculating any of the missing either 1, 3, and 2, 4 Kennedy lines. So let's go and find instant center 2, 4. I need to operate with the Kennedy line 2, 3. Let me pause again and label these as I, 1, 2, I, and so forth. Okay, so now I have the instant centers labeled, and we said that we're going to find first instant center between 2 and 4. So let's draw the Kennedy line. I'm going to use different color. Kennedy line 2, 3, and 3, 4. So I need to connect 2, 3 with 3, 4, which is infinity. Essentially, it's a matter of drawing a perpendicular line perpendicular line that is parallel to the reference that I had here, and then the other Kennedy line. So this was 2, 3, 4. Let me even say 2, 3, 4, 2, 2, 3, 4. And then so this was 1, and then the other Kennedy line would be 1, 2, 4. So I take 1, 2, and then connect 1, 2 with 1, 4. And let's see, so it'll be like this. Select all, and I would have to extend both of them until they intersect. Okay. Ooh, I wanted to erase some junk. Okay, so where the two lines intersect, I have the instant center that was missing, I 2, 4. 2, 4 I said. Okay, so I 2, 4, come on. Rectangular selection. And it's right here. So we've got it. We celebrate this on the circle diagram. And let's look at the other one, I13. And for that, we're going to operate with, I'm changing colors again. It's dark or brown. So it will be Kennedy line 1, 2, 3. So I'm connecting 1, 2 with 2 3, 1 2 with 2 3. This actually can be moved. 1 2 2 3, and then I have 1 4 and 3 4. So 1 4 connected with 3 4. So what I need to do is again draw a perpendicular. Let me copy this for convenience. Copy, paste. Paste again. Okay, so back to the line tool. I'm now drawing the Kennedy line 1 2 4. So I think I did something wrong. So 1 2 and 1 4. I drew 1 2 3. I lost myself. It's almost 7 o'clock. Let me take a break and we'll fix this. All right. So I got myself confused by looking at the blue line. Actually, we're working with, after the we're missing. It's the corresponding to the dash line I13. We drew Kennedy line 1 2 3, and then we need to draw Kennedy line 1 3 4. So 1 3 4 would be the 3 4 line. I said 1 3 4, so the rather connecting instant center at infinity at 3 4 with 1 4. So that's why I drew. I took these and represented perpendicular to the line of sliding. So using the current color and thickness was, I believe, this one. So let's draw the Kennedy line, and we're going to move it to where intersection occurs. All right, and we have the second instant center. So let me move it where it's not going to bother us, and this is the last 6 of the instant center, I13. Okay. So we have all of them. We can make this line solid. Okay. So we've got the 2 missing instant center, 2 4 and 1 3. All right. For the gear pair here, we can do the same. So I go to paste, transparent, no, select all, pause. Okay, so we have a system of 3 bodies, a gear pair, and we want to find the instant center between the 2 gears. This is called the line of centers. We have the contact point between the 2 teeth somewhere here. We can draw the common tangent easier, and then the common normal. Okay, and this is where the instant centers between the 2 gears is. This is also called pitch point. So when we'll start involved gears, we'll refer to this as pitch point, and it's essential in order to transmit constant ratio between the 2 gears for this point not to change location. This is the fundamental theorem of gearing. an application where you have more information that you need and you find a mechanical advantage. And then other applications, calculate mechanical advantage of some garden shears. You need to decide which one is the ground, and it could be the blade. And how many bodies do we have? We have ground, 2 and 3 bodies. Decide where contact is made at this at the gear sectors. Note that they are not circular; they are not concentric with the pin joint. Neither is. And you can include in the mechanical advantage analysis, although not showing this figure, or I cropped the figure, the effect of the arm length. This is another garden shear. Thank you, China, for taking care of the needs of gardeners. And here we have a pin in a curved slot. But again, there are how many bodies? Ground, 1, 2, and 3. 3 bodies. And so let's look at this one. I'm going to, I would say, we looked at something that looked like a gear pair. It will be this case. Let's look at this one now. So I take a screenshot. Let me make it a little bit bigger, and we're going to evaluate mechanical advantage in terms of for this garden shear. So print screen and paste. Select all. Okay, and I'm going to just delete everything else. Okay, so you need to label links and joints. So this is the line of centers, like right there, and then we have so the 2 ground joints, and then we have here a round pin. I need to figure out where the common normal is. So I would have a common tangent, maybe something like this, maybe. Okay, and then a common normal. Try hard to make this perpendicular. I can use a business card, put it on the screen. You can't see this. To make this, yeah. So use the business card as a square. Okay, and then extend this. Okay. Hey, come on. Wow. I want to draw a little circle. Okay, so this would be the instant center between the other handle and the blade. And I could assume a force, operator force, and I could assume this to be at the length of the arm, so I would be able to measure, distance from the point of application to where I'm interested in. And then I can also assume that I'm cutting some branch. So I have a branch and I'm cutting, and I can tell the resistant force to cutting and make thinner. Okay, so imagine you work for Fiskars. It's an American company that does this kind of gardening equipment, manufactures a number of products for home and garden. Copy, paste. I'm trying to get rid of this. Paste, okay. Okay, so this is the input force, this is the resistant force. We can what we'll be interested in knowing what's the ratio between the resisting force and the operator force, so what else do we need? We need to know, like this, or rather the arm of the force, calculate the moment, and then arm of the force of this other force to calculate the moment. So it would be like this distance from here to here. I need to switch to what? To a cursor. Okay, so distance from here, let me switch here. So this distance would be the arm of the operator force, and this distance is going to be the arm of the resistant force when cutting this kind of branch. And what I would need to also find is so that will be the blue lines allows us to calculate the moments, but the input, the resisting moment. And then with the instant center between the two bodies figured out, we can find the ratio of angular velocities, and ultimately we can find the mechanical advantage for this shear. Okay, so I guess this is it. I could spend additional time finishing this, and I can post it for you, but otherwise I would say this is a materials covered, and you'll see some homework assignments out of this. All right, well, thank you for watching.